Find the area of the region bounded by the graph of the function f of x equals 3x squared plus 1, the x-axis, and the lines x equals 0 and x equals 2. Okay, so let's see what we're working with here. So we've got the parabola 3x squared plus 1. So looks something like this. The x-axis, so that's this. The line x equals 0, which is this, and the line x equals 2, which is about right there. Okay, so it looks like the area we're looking for is right there. Okay, so let's actually draw it a little bit neater. So now that we know what we're looking at, all right, so here's the area we're looking for. And we're going to use a Riemann sum. And as I mentioned in a previous video, algebraically, it's a little bit simpler to use right endpoints rather than left endpoints. So a generic rectangle, or the ith rectangle that we're going to use to approximate the area, it's going to look like this. So the height is f of m sub I. This x value right here is m sub I, capital M for right endpoint. And the base of the rectangle, or the distance from here to here, that is delta x. So this length of the base is delta x. All right, so delta x is equal to b minus a divided by n, or the length of the interval divided by n, which in this case is 2 over n. So that's the base of the rectangle. The right endpoints. So these are the x values that we plug into the function to get the y values, which is the height. So each of these m's we plug into the function, and that gives us the height of the rectangle. So this is the base, and capital M sub I, well, our formula that we developed for this is a plus I delta x, which in this case, a is 0, because that's the beginning of the interval. The interval is 0 to 2. And delta x is 2 over n, so a plus I delta x in this case turns out to be 2I over n. Again, this is the x value that allows us to get the height. So let's say the height of, we'll say it's the ith rectangle. So that's f of m sub I. So we plug 2I over n into our f of x function. So that's 3 times 2I over n squared plus 1. And so 2 times 2 is 4, times 3 is 12, so that's 12I squared over n squared plus 1. And that's the height of the rectangle. So now we have an expression for the base and the height of each rectangle. All right, so now we could talk about adding all of those rectangles up. So the next thing we're going to do is the approximate area. So before we apply limits or anything like that, the approximate area is going to be equal to the summation I goes from 1 to n, because we're adding up n, the area of n rectangles, where the area of each one of those rectangles is the 12I squared over n squared plus 1, that's the height, times the 2 over n, that's the base. So height times base, or you could do base times height. The order doesn't matter because it's multiplication. All right, so let's see if we could do a little algebra here. Let's multiply out. So it looks like if we multiply the 2 over n to each of those terms, we'll have the summation I goes from 1 to n of 24 I squared over n to the third. So 2 times the 12i squared and n times the n squared, and then plus 2 over n times 1. And we could split this up using properties of summations. So we're basically applying the summation to the first term and then separately the summation to the second term. And the 24 is a constant and the n cubed is a constant. So we can factor out the 24 and the n cubed and leave the I on the inside. So that's times the summation I goes from 1 to n of I squared plus the summation I goes from 1 to n of the 2 over n. And the 2 over n is a constant. All right, so let's apply some formulas that we've developed previously. So this right here, we have a formula for that. And so we'll come down here. So that's equal to, well, we've got 24 over n cubed on the outside times the summation of I squared, or the first n squared numbers. That's n times n plus 1 times 2n plus 1, all divided by 6. And then for that second summation, the summation of 2 over n, well, 2 over n is a constant, so we're adding 2 over n plus 2 over n plus 2 over n plus 2 over n times. So that's 2 over n times n. All right, so we could do a little bit of canceling here. Well, these n's cancel, definitely. 6 and the 24 over 6 is 4. This n cancels one of these n's, so that becomes n squared. And I think that's about all the canceling we could do. So that's 4 over n squared times, and let's FOIL this out. Let's multiply this out. So that's 2n squared plus 3n plus 1. And then we've got a plus 2, just plus 2 because those n's canceled. All right, so now we could multiply through the 4 over n squared. So this is just a good amount of algebra we're doing here. So we multiply the 4 over n squared, we'll get an 8. We'll get a plus 12 over n. We'll get a plus 4 over n squared, and we've got a plus 2. And 8 and 2 is 10, so it looks like finally in this simplified form, that's 10 plus 12 over n plus 4 over n squared. So that is our area, or our approximate area, using n rectangles. Approximate area using n rectangles. So now, if we want the exact area, we just let the number of rectangles go to infinity. All right, so the exact area. So the exact area is equal to the limit as n goes to infinity of the summation I goes from 1 to n of f of mi times delta x. So the summation portion is the sum of the n rectangles, and then we're taking the limit as n goes to infinity. And we've already done the simplification. So that summation is equal to 10 plus 12 over n plus 4 over n squared. And so now we can take the limit equals the limit as n goes to infinity of 10 plus 12 over n plus 4 over n squared. And 12 over n, as n gets big, 12 over n goes to 0. 4 over n squared goes to 0. So this is equal to 10. So 10 square units is the area bounded by the graphs of f of x equals 3x squared plus 1, the x-axis, and the vertical lines x equals 0 and x equals 2. All right, that does it for this example. I hope it was helpful.